So, hi everybody. I'd love to introduce Noah Planavsky from Yale University, who is looking at various well, rock weathering processes, in particular, hence rock weathering for carbon dioxide sequestration. Welcome, Noah.
Great. Thanks so much for the invitation, and happy to be able to share some of our work with you. All right. Yeah. So going to walk through some of the aspects about the modeling of enhanced weathering that we know, and also try to highlight some of the aspects where we have gaps in our knowledge, or we are still developing a modeling framework for enhanced weathering. So enhanced weathering, first of all, to start out, what is the very basic idea of enhanced weathering? The fundamental idea behind enhanced weathering is that you can take quarried material, mined material, in most cases material that is waste products from mining, and apply that to agricultural settings in a way that both improves the quality of the soil, is beneficial to farmers, and results in permanent carbon dioxide removal. So enhanced weathering at the most basic level is a means of durable or permanent carbon dioxide removal on long time scales that takes a waste product and uses the infrastructure from farmers. That's the basic idea of it. What we'll do through the talk is develop what are the aspects you need to understand to be able to actually use this process to make compensatory claims for carbon dioxide removal, or to be able to understand what are the carbon fluxes associated with this process even. Okay, so before any time we talk about carbon dioxide removal, I think it's beneficial to first ask, why are people talking about carbon dioxide removal? There are a lot of varying views on carbon dioxide removal, and before getting into it, I think it is always important to set the stage for what are aspects of what carbon dioxide removal can do, how can it play a positive role in climate change mitigation scenarios, and what it can't do. So as a first and most basic aspect of carbon dioxide removal is not and should not be discussed as mitigating emissions reductions. We need dramatic emissions reductions to meet any sort of climate goals. If those aren't first and foremost, we're never going to meet climate goals. However, if we want to meet international climate goals, on top of even the most aggressive emissions reduction scenarios, we also need to remove carbon dioxide from the atmosphere, carbon dioxide removal. So this is one way to illustrate that point. If we want to meet some of the goals from the Paris Accord, keeping carbon dioxide at 1.5 or degrees of warming, or keeping carbon dioxide even at 2 degrees of warming, not only do we need to rapidly move to near zero emissions, we actually need to have net negative emissions to meet those climate goals. So when folks talk about carbon dioxide removal, the other way to set the stage for this is carbon dioxide removal has to be part of a broader portfolio of ways in which we are controlling greenhouse gases at a global scale. They can use to help offset historical emissions, they can use to offset hard to abate sectors, but they are not meant to be viewed as a replacement for traditional mitigating strategies. We are at a point in terms of our climate trajectory where to meet any sort of goals, where to meet the thresholds we're beyond if we cross them are going to cause economic damage, damage to human health, damage to natural ecosystems, we need to be thinking about how traditional mitigation technologies are coupled to large-scale carbon dioxide removal. And the types of amounts that we're talking about for carbon dioxide removal to meet these climate goals are very large. We are talking about removing potentially billions of tons of carbon dioxide removal to have no or limited overshoot in our climate goals. And it's important to highlight in this as well that when you see these scenarios, that they are in many ways, I think, optimistic, because when we're talking about having massive amounts of carbon dioxide removal, that is taking a fairly optimistic scenario on how other greenhouse gases will change through time, assuming that we are able to curb the other greenhouse gases that we have, many of which are tied to the agricultural sector. And of course, it could be difficult to meet some of the goals of reducing emissions from the agricultural sector on top of increasing global population and global food demand. Okay. So that's very much just setting the stage for why we're talking about carbon dioxide removal, but I think is an important thing to highlight as well. One of the other things that's, I think, important to preface with when talking about carbon dioxide removal is there has been a large amount of negative press and coverage on carbon dioxide removal, and this has come from multiple different avenues. There's multiple scenarios where you could highlight where there have been carbon dioxide removal projects that ended up providing very little climate benefit. Many of the most well-documented cases of these are in aspects that are dealing with organic carbon storage in natural environments. So one of the ways the other preface for why we're talking about carbon dioxide removal is carbon dioxide removal through enhanced weathering provides an alternative to what is the traditional voluntary carbon marketplace, where it's much more difficult to predict the fate, the long-term fate, and the effectiveness of your carbon dioxide removal strategy. So as we'll develop here, enhanced weathering is a reliant on geochemical reactions instead of the functioning and the time trajectory of natural ecosystems. And that provides one way to potentially make credits less debated and more robust. Okay, so what is enhanced weathering? Give you the basic overview from this, but I think the talks about how we actually model this process will be more fun if everybody feels more grounded on what are the basics of this process. So the basic idea can separate this out into several steps. The first step is that you deploy a rock that has an ability to suck up CO2, ideally in many cases in an agricultural setting. That silicate rock, basalt is the most common example, one of the things we'll talk about in detail, is able to lock up atmospheric CO2, which moves from a gas form to an aqueous form as bicarbonate. That is an aqueous form of carbon. So when we're actually doing this in scale, the next step of this is actually measuring the amount of weathering that has happened. Quantifying the amount of weathering that's happened is a big uncertainty in this process. Next, if we want to think about what happens and how this will tie into our accounting framework, we have to trace the weathering products as they move from soils and into rivers and into oceans. And then we want to track the long-term fate of the carbon as well. When I said it's permanent carbon dioxide removal, we want to be thinking about not what's happening on a decade scale. We want to be thinking about what is happening on 100, 1,000, or even a 10,000 year time scale. Okay, so some folks, I would say myself included, are not going to feel comfortable understanding a process unless they can see the grounding equations behind it. So we're going to walk through the actual basic equations that ground all aspects of enhanced weathering. Okay, so the first step is this carbon dioxide will interact with a water phase to form carbonic acid. This is going to be a reaction that is basically always going to be in equilibrium. You'll form carbonic acid. Carbonic acid, as the name suggests, is a weak acid in an aqueous species that can interact with any number of rocks, minerals that make up the continental crust. So carbonic acid will interact, for instance, with a calcium silicate, and that will produce dissolved species, the calcium and bicarbonate. The bicarbonate is directly related to the CO2 and the carbonic acid from this reaction. Okay, so these dissolved ions are then transferred into rivers. Rivers will transport these into the oceans. Okay? So the simple way to think about this in a summed sense is that you have calcium silicate that combines with carbon dioxide and water to form, in the ocean side, calcium carbonate rock, resulting in something that is stored for millions of years and net CO2 removal. This is the simplified reaction of those after the weathering products in the oceans over thousands of years combine to form calcium carbonate.
So question,
yes.
what's the pH of the result? I mean, me ask is because when ocean normally absorbs carbon, that's makes it more acidic, correct? You know, if I'm getting it right. So what is the effect of this thing?
Yeah, great question. So what you're doing, kind of think of, and here is you're actually putting more calcium and bicarbonate in the ocean. So this is actually, enhanced weathering is one way to deacidify the oceans. You actually are adding more, when you have reequilibration of the weathering products moving into the ocean, it gives you an increase in the carbonate saturation state and an increase in pH. So one of the things when we worry about the suite of problems related to unmitigated greenhouse gas emissions, having warming is obviously a big problem, but having more CO2 move into the oceans and causing acidification is a problem. Enhanced weathering is one that both can limit CO2 concentrations and one of the few ways in which we can also deal with ocean acidification.
And just to be clear, this process is for capturing atmospheric carbon, but do you have something, I mean, is that correct, first of all? And because my question is, what about making the oceans more effective as carbon absorbers? I mean, because it sounds like a similar kind of thing.
Yeah, so in this case, when you're thinking about enhanced weathering in, say, agricultural settings, one of the aspects that makes this a really quick reaction is that the CO2 concentrations in soils, so your carbonic acid concentration in soils is going to be very high. So you can think of soils, or one way I like to phrase this is you can think of soils as basically large-scale bioreactors. In soils, it's commonly 1% CO2 in the gas phase instead of being parts per million like it is in the atmosphere. So this reaction will be soaking up CO2 from soils that are in a very high concentration and then delivering the weathering products into the oceans. And that's different than ocean alkalinity enhancement, where you're actually trying to either add base to the oceans and get CO2 to move into the oceans. So ocean alkalinity enhancement and enhanced weathering are two fundamentally different processes, but it's the same basic idea where you're trying to introduce cations into the system, really, which get balanced with bicarbonate to give you charge balance.
Got it. Thank you.
Yeah. And of course right. So one of the things when you think about all aspects of the carbonic acid system, it can seem, and I feel there's a lot of kind of confusion about the carbonic acid system. The simplest way to think about it is that the carbonic acid system is really just the expression of charge balance on the Earth. So tracking what's happening with cations, which will be charge balanced, and in most cases with bicarbonate, is the simple way to think about that. So it depends where you're adding cations and what is the effect of that in a soil, in a river, in an ocean. Great question. Okay. So the weathering products mentioned before will eventually move into calcium carbonate. This happens in very long time scales, gives you the permanent sink of CO2 from the atmosphere. And all of those reactions can be simplified together to give you this, what is often referred to as the Urey reaction. So the Urey reaction is the chemical weathering of the crust followed by calcium carbonate burial in the oceans. This transfers carbon to the atmosphere into the rock reservoir. And this is the reason that the Earth is habitable. The same process removes naturally about 1 billion tons of CO2. What we're trying to do for enhanced weathering is dramatically speed up using infrastructure associated with mining and agriculture to make this process more rapid, to make this process, to increase the scale of this process. All right, so when we think about tracking enhanced weathering, what this actually looks like at scale, and now to get into what are aspects where modeling plays an essential role of us understanding this process. What we have to do to really understand the fate of and the effectiveness of enhanced weathering is we have to understand what's happening at the field and soil scale. So that is reactive transport modeling in soils. We have to also understand what happens in catchments, in rivers, in surface waters, and then we have to understand on both a short and a long time scale the fate of weathering products as they move into the oceans. So what we're going to do here briefly is walk through some of the modeling tools that we use to understand each of these steps. Models to understand what happens in soils, models to understand what happens in rivers, and the modeling framework we use to understand ocean storage. We will leave some time at the end as a kind of fun one, though, to talk about a way in which we can talk about this process, not in agricultural settings, but in a more, I think, underappreciated setting as well, as a teaser for folks to stay interested through the end. All right, so setting the stage before we get into too much modeling on also why you should be excited about enhanced weathering, not just what are the basics of it. We have empirical results now that suggest that enhanced weathering can be relatively effective on a field scale. This is kind of what primes why we want to think about developing a sense of modeling framework to think about this in terms of the long-term fate of it. So we can remove, this is a study from University of Illinois experimental farm. We have extensive greenhouse gas removal on a per acre, per hectare scale over multiple years, and associated with that, we have a statistically significant increase in the yields, the grain yields in a corn-soy rotation over this same period. One of the other reasons to be thinking about this, setting the stage for why we're interested in this, is that when we think about, this is a very busy slide, but when we think about the main takeaway from this is when we think about the potential benefits of this to farmers, which is one of the ways to think about the real potential of this process to scale. Overall, soils are very acidic. So this enhanced weathering process is a way to deal with that acidity, which is going to decrease, which the acidity is decreasing agricultural yields. So similar to what I just showed you on the first scale for seeing a significant agricultural increase in agricultural yields associated with the enhanced weathering process, that is likely to be widespread. Any of these areas expressed here in red are areas that would be prime targets for enhanced weathering to scale and where it's likely to have a significant agricultural benefit. And as a last one, the price of this process and the potential to scale are both pretty high. So one of the main advantages of enhanced weathering, it doesn't use new land, doesn't have major amount of capex to it, requires very little energy. So when you think about predictions from companies that exist right now, if we can figure out the effectiveness process, we can have an effective large-scale modeling framework to support this process, there is a potential to have a significant number of carbon dioxide removal credits in a scale, in a cost that for robust carbon dioxide removal is potentially economically feasible in a decade or less scale. And as lastly from this, one of the things that's important to keep in mind is this also fits very closely with goals of current administration, but goals of federal government, where it's a way to both drive carbon dioxide removal and support rural communities. And part of that is that this plays a large role in supporting farmers, as already stressed. So it's a way of leveraging American agriculture to reduce greenhouse gas emissions.
So question, you were just showing the reductions in costs from what ERW, that is going from 350 down to what 90 in about 7 years. What's the benefit of the lime? So it would be replacing lime. So what's the economic benefit of that to kind of overcome some of the costs?
Yeah, great question. So lime is an interesting one where it's by the IPCC, for instance, is listed as a carbon source, but it plays the same role as enhanced silicate weathering, where it can deacidify soils and give you increased agricultural yields. So the geochemistry behind whether liming is a carbon source for sink is actually a little bit complicated. But the simplest way to think about it, if you take the IPCC framework, is what enhanced silicate weathering does is it replaces a carbon positive product with a carbon negative product. And it also, because you have this added benefit, is a way for farmers to be able to more readily, while still making a profit, control the pH of their fields.
So now, I mean, I'm assuming that they currently buy limestone and that they transport it and whatnot. So
Yeah,
what's the, I guess, if farmers were to pay for this pH controller as opposed to limestone, how much would they pay? And then does some of the costs you were describing?
Yeah, well, right now, the way a lot of the companies that are doing this at a commercial scale and the way that a grant through the U.S. Department of Agriculture that we have set up is, instead of them paying for lime, we are covering all of the costs of the salt application to their fields. So they're getting the same benefit of soil deacidification, but all of the costs of that are covered. So limestone application to their fields is a cost to them, whereas adding silicates to their field is has no cost.
Okay, makes sense. And then, as
and
a
of course,
one,
long term how that plays out is long term how that plays out is going to depend on markets, how markets shape up, what is the cost of carbon, federal policy changes, etc.
Right. And then how does this interact with biochar? Because that's the other soil amendment that does, works completely differently, benefits and, completely differently.
Yeah, but I mean, they can be co-applied, and that can help. One of the things that can actually help reduce application deployment costs in the system.
Makes sense.
Think of it as very much complementary to biochar application, and another tool that farmers can use to turn agricultural settings from being a major greenhouse source into being a greenhouse gas sink.
Got it. Thank you.
Right. Okay. So getting into some actual modeling work, we're going to walk through again kind of the basic idea of these. And of course, we could have a whole hour on each on each of these modeling frameworks. We wanted to introduce this is just what are some of the tools that we use to think about the carbon fluxes through these systems. So one of the first way to start is obviously in the soils. The basic idea behind tracking weathering flux or weathering processes, the consumption of CO2 in soils is something that has been around for a long time. We have, for instance, working with folks at Georgia Tech, led by folks at Georgia Tech, have built a new reactive transport model in the soils that's designed specifically for enhanced weathering. But the basic idea of this is relatively simple. It's a partial differential equation that tracks both transport of fluids and then tracks geochemical reactions. So there's some aspects of this that it does a very good job of predicting. If you can prime it with weathering rates, you can have a high certainty that it will track the fate of those products in the reactive transport model. One of the things that it does not do a great job of necessarily is tracking the actual rate of silicate weathering. That's something where if you compare different models at this stage, if you compare different models, they will give you, depending on the assumptions you make about how feedstocks, the rocks that you add to the soil, change over time, will give you different answers. So kind of the knowns of thinking about modeling enhanced weathering from the soil scale, we can come up with fairly good potentials of enhanced weathering at the scale. We can think about what sort of amounts of cations moving into systems will be needed to modulate soil pH. That's the example showing here, how you can take the boundary conditions and an amount of acid production in a region tied to agricultural practices and think about what it takes to neutralize that acid. But what these models at this point cannot be used for is for the actual monitoring, reporting, and verification of deployments. So Reactive transport modeling in soils is a great tool to help us plan and optimize deployments, but right now it can't be used to provide an accurate, a robust estimate of how much carbon dioxide removal capture, how much carbon dioxide removal, how many carbon credits could be issued for deployment without any supporting empirical documentation. So this is as many models, if you think about the fate of modeling endeavors, this is a stage where there's a whole bunch of individual models, and right now working on model into comparisons to really flush out how robust these models are and how we can come up with a coherent message from, I think, a group of models rather than an individual model to predict the fate of weathering products.
And question, is the uncertainty that it's the local weather or local soil or some other uncertainty?
Yeah, great question. I think the main uncertainty, as I said before, and one of the ones where I think we need empirical support for it, is you're putting a feedstock, right, the rock that's going to consume the CO2 into the soil that has a set initial characteristic. And one of the things I didn't stress enough before is that it has a really high surface area that will allow it to rapidly absorb CO2. That's kind of the key aspect to this whole process. But how that surface area and how this rate of CO2 consumption changes through time is the uncertainty. You can have really rapid initial rates and then have that process significantly slow down as the weathering proceeds. So the parameterization of how the feedstock changes through time is something where we don't have, in a diverse range of settings, a sound understanding at this point. The basic aspects of these models, of these reaction transport models is very solid. The actual weathering component is something that has large uncertainties. Where we can, with additional empirical information, can try to develop a more robust, more standardized parameterization for that process. All right. Yeah, great question. Thanks. So the next step is obviously once you have weathering occurring, the weathering products will move into a river network. And this is one that I'm going to spend a bit more time on. This is one that is very excited about. This is work doing with folks at Texas A&M, Chuang, and folks at Georgia Tech, Chris Reinhardt. So the basic idea is that we want to be able to track the fate of all weathering products in any surface water, ideally anywhere in the world, but we're going to start and walk really through how we would do this in the US. So the first aspect from that is you need to have the drainage pattern or actual surface water patterns be emergent. And this is something that we're actually very good in. This is something that we've been good at for quite a while now. This is an example of all of the drainage networks that evolve, largely building from really high resolution topography networks. This is a little bit difficult to view. So an easier way to view this is by looking at drainage patterns where you remove the smallest surface waters and just focus on the larger patterns. And this is, of course, showing the US's largest catchment, the Mississippi. The next step from this is, if you want to track the fate of weathering products in ocean, you have to understand your actual physical river network, but you also have to understand the geochemistry of that river network. So to do this, we built from very large empirical data set, about 6 million, reasonably large empirical data sets, about 6 million individual data points for both physical characteristics of physical and geochemical characteristics of river waters. And we used a machine learning framework to be able to have we used a machine learning framework to transfer with known boundary conditions the chemical composition onto the physical river network that emerged from that system. What that does, it allows you in any surface water in the US, be able to predict the carbonic acid system predict how carbon would behave in that surface water. And given that it's a reasonably large, dense data set for the US, this behaves very well for the US. Data is less dense for the rest of the world. So of course, your uncertainty, even though you could apply the same framework, is less robust when we move outside of North America for this process. One of the aspects that this allows us to do is this allows us to ask, what is the capacity of rivers to carry the products of weathering before we have secondary chemical reactions that would release the carbon back to the atmosphere? So this we can think of as a carbon transfer potential. And this is thinking about, is the simple way to do this, to think about this number, is it is asking not how much weathering could occur in soils, but assuming that that can be unlimited, how much could rivers carry? How much of the weathering products could rivers carry to the oceans? And it's thinking about this really from a sense of what is the saturation state or the omega value of the secondary mineral products that release carbon back to the atmosphere. And the main takeaway from this is, without getting too much into the details, is that when we do this both on the US scale and on the global scale, we note that we have with any reasonable assumption about when we will release carbon back to the atmosphere, we will have a very high potential for carbon dioxide removal through this process. So in the US, this is, I would say, his best guess, somewhere around half a gigaton of CO2 per year, and globally, this is going to be above 5 gigatons CO2 per year. So the important aspect from that is this is an indication that it is unlikely that the rivers are going to provide a limiting step in the potential of enhanced weathering. One of the other things we can do with this, which you can't do with a static river network, but you can do with a dynamic river network, where the components of the weathering actually flow through the river system, is ask how much, if any, carbon leakage will there be during this process? So there is the potential to have loss of carbon after it leaves the fields. If you're going to make compensatory claims, you need to have a strong understanding of that process. Okay? And so the simple framework for this is that the same idea that we developed before. You have, from elevation patterns, you have a river network evolving. You use a machine learning framework to predict, with a given boundary condition, the chemical characteristics of water in any portion of the US. And then to think about this in a dynamic sense, we split up every water mass into a series of very small segments. And then we can place those into a simple series of differential equations that allow you to add weathering products to the river network and allow you to have, as water fluxes, as precipitation on a country scale changes, have those products move through rivers and into the oceans. And the main ones for this is we're tracking the cations, the calcium, for instance, that moves through the system, and the components of dissolved inorganic carbon, the bicarbonate and the total dissolved inorganic carbon package in the system. So this is one where it's often, very rarely do you build models and things turn out better than you expected. Although I should say this is something that happens to me more often when I work with one of the folks that is leading this, Shuang Zhang, who's an amazingly gifted modeler. So this is a result from a single point here, showing you how the model behaves relative to actual empirical observations. So the numbers here are the different number of segments, river segments, that the water masses will transfer through. So 200, 400, 700, 771 segments. This is the longest flow path in terms of number of segments that we've separated it to within the Mississippi River catchment. And what you can note is with the graphs here show is that in any one segment, we can do a great job of, through time, predicting when forced with weather patterns, climate, how the aspects of the carbonic acid system, how dissolved inorganic carbon actually moves through rivers. What this can also allow us to do is then, instead of thinking about this as a single point, what would happen if enhanced weathering was scale, you would have people adding alkalinity at a whole bunch of different points. So we can also, in this, add alkalinity, not in thinking about a single point, but thinking about how the system will respond in a wide range of different environments. And specifically what we're interested in this is thinking about how this changes the carbon degassing in the system, right? This is what will determine if there's any leakage, carbon leakage out of the system. And what we see from this is that degassing rates are highly variable in different settings. You think about this at the time after deployments. But overall, if you think about this relative to the background condition without any alkalinity deployment into it, there is a relatively small amount of carbon loss associated with this carbon addition. So this is the percent of loss of carbon that we would have captured in the field, and it is a really low number, only 5% of the carbon. That is an inefficiency that is relatively easy to deal with in terms of the overall cost of your enhanced weathering process. So dynamic river network allows us to have robust tracking of river degassing across a wide range of scales. And this only gives us, in most cases, a relatively small amount of loss of carbon from this system.
So question actually, to what extent does groundwater transport play a role here?
Yeah, great question. So groundwater is one of the main aspects of groundwater is that it will affect it'll be in this first part where you kind of have reaction transport models that determine how long it takes for the weathering products to move through soils and into rivers. And in some cases, of course, if you have things moving like into permanent groundwater storage, greater than 1,000-year groundwater storage, which is a relatively small amount of waters, then that's great. You get to forget about the complication associated with waters moving through rivers and waters moving into the oceans.
Okay, so is the delay due to groundwater transport an important component of this, like changing the season? Like if it takes 6 months, it's very different precipitation pattern, or is it just wash out?
Yeah, it's a great question. It's the way to think about it is that there's going to be a delay there's going to be a significant delay, somewhere from months to, in some cases, years of weathering products moving through the soil. And that's kind of what this first aspect of the modeling helps you understand.
Yeah, thank you.
Question. All right, so to finish up here before we finish up on the other frameworks, what happens when the components of weathering move through soils, move through rivers, and then move into the oceans? So to get at this aspect of system, there's a wide range of different ocean models that you can explore for this. One of the ones that we've been exploring, which is meant to kind of be illustrative of what is possible from this, is using a model called CGenie. This is an intermediate complexity model. So it is functions essentially as a GCM, but is a relatively short runtime that allows us to, or is more computationally effective, that allows us to do explore air in I think a more meaningful way than more computationally expensive ocean models, and also allows you to explore not only what happens on a 1 to 10 to 100-year timescale, but also what happens to the fate of carbon on a 1,000-year timescale, which is similar to the atmospheric lifespan of carbon. So the framework for this is relatively straightforward. It has an atmosphere that doesn't interact with an ocean, although that interaction doesn't change through time, is one of the things that allows this to be more computationally effective. And one of the aspects of where CGenie really, I think, in the version of this that we're using, is useful for is that it does a very good job of parameterizing how dissolved inorganic carbon moves through the ocean system. So even though this is a relatively simple model relative to many of the more complex GCMs, it does a very good job of predicting historical and future climate change relative to kind of the CMIP class models. So this is showing, for instance, how the model behaves in a series of stochastic runs relative to model in a comparison, climate model in comparison CMIP5 runs. So one of the things that, as I said, I already alluded to this, one of the things that we're really excited about from this is this, one of the large uncertainties when you think about what is the long-term fate of a carbon dioxide removal project is how the Earth system will respond to that. And a large portion of this is actually how the terrestrial biosphere will change with a change in emissions or a negative emission technology. And to be perfectly honest, models right now have a fair amount of uncertainty in this. So by using this modeling approach, we can actually use a stochastic approach to estimate the uncertainty associated with any carbon dioxide removal project using filtering results from the more complex models from this, what people think of as the kind of state-of-the-art GCMs that are in the CMIP project. So this is just one example for this, showing how our stochastic representation at a given emission scenario tracks land carbon relative to the results for the model in a comparison project. And the simple takeaway from this is this allows us to have a way to think about air in an Earth system response to a carbon dioxide removal project or a large purchase like Alphabet would make, for instance, in a meaningful way, more meaningful way to quantify air. So here's some results of this showing an actual large-scale deployment, comparing a base scale to having a large-scale enhanced silicate weathering case. And one of the things that you notice from this, the basic takeaway from this, is that, as you would have alluded to, we end up close to major river mouths, increasing the amount of dissolved inorganic carbon that we have in the oceans. And we have some amount of increased carbon degassing in particular regions from the deployment of alkalinity moving from rivers into the oceans. But this actually allows us, the modeling framework allows us to ask how much of an uncertainty or how much of a inefficiency is this process through time. And the inefficiency specifically associated with the enhanced weathering case, the amount of leakage that is occurring in the ocean, specifically relative to dissolved inorganic carbon moving to the oceans, is relatively small. It's on the scale, regardless of emissions trajectory, which is interesting, of around 10%. The gray bar here, which shows leakages, is the whole Earth system response to different changes in emissions, in emission reduction trajectories. Okay. So the takeaway from this is that a large ensemble ocean model approach yields a relatively small amount of system loss for enhanced weathering products from the ocean, somewhere around 5–10%. And one of the other things that's important to stress as well is that if you have leakage in river systems, that will decrease the amount of carbon leakage that you have in the oceans. In both cases, the carbonic acid system is adjusting. And one of the other key takeaways for this is the system loss is relatively scale independent with respect to CDR magnitude, which is a key takeaway for thinking about the practicality of this project. So the takeaway from both the rivers and from the oceans is that obviously if we want to think about enhanced weathering scaling, we have to understand what's happening in the field, but we also need to understand what's happening in the rivers and the ocean. That's only going to come from a modeling framework. That's something that had been a large gap in our knowledge before. And what these tools that we developed over the last couple of years suggest is that although you certainly do have carbon leakage in rivers, in the oceans, associated with this type of carbon dioxide removal, the amount of leakage that you have is actually relatively minor, something that's not going to dramatically change the cost. It's likely something that is a 10% efficiency instead of a 20, 30, 40% inefficiency in this process. And importantly, is something that we can have air-bounded estimates of, which are essential for thinking about how this process would ever be put into a market, how you would ever have contracts for the extent of carbon dioxide removal associated with that process. All right, so that's the modeling framework that we have. To end up here for the last couple minutes, and I have a fun idea and an idea of potential collaboration with folks. When I was talking about enhanced weathering, where most commercial efforts right now, where most research efforts for enhanced weathering right now are focused is on how we can take these mine products, these mine waste products, and move them into agricultural settings. There are obvious reasons to do that, as I mentioned before, where it can have significant agronomic benefits. But one of the other ways in which we could, given the massive potential that we have for this process, where we could think about utilizing this is in roads. So this is a map that is showing from Bell, that is showing the network of roads in the U.S. An easier way to think about that from the U.S. is thinking about that for something for folks at Alphabet that is more close to home, thinking about the Bay Area, showing the network of roads. Obviously are very dense in areas we expect, more sparse, luckily, in some portions, as you would expect. Even in agricultural regions, you still have this incredibly dense network of roads. That is found not only in the upper Midwest, but also in the Southeast and in the eastern seaboard portions that are dense agricultural regions. These roads, in many cases, could be areas. It is a shocking amount of our surface is a massive. As those images, I think, do a striking job of illustrating, is a tremendous amount of land. Many of these settings could be utilized for enhanced weathering. So, for instance, if you think about having medians and in more natural areas along the edges of roads could be prime targets for enhanced weathering. However, not all roads obviously are going to be ideally suited for that. So to be able to think of an estimate of an estimate of the area that could be utilized for enhanced weathering, we need to be able to have a way to distinguish areas that would be ideally suited, road settings that are ideally suited for enhanced weathering, and areas that, for obvious reasons like urban settings, would not. This is something that would be I think a really fun exercise to get after through something using the resources that we have from Google Earth imaging and the massive amount of compiled and much more accessible satellite imagery of landscapes than we used to have. And one of the other things from this that's interesting one to stress is that, of course, there's a fair amount of infrastructure that already supports the maintenance of these settings. For instance, salt trucks could be salt trucks that are often owned and are infrastructure that is not utilized in the summer, or tractors that are associated to maintaining our roadways could be turned into could be infrastructure that could be utilized to have enhanced weathering in these settings. leave that as a I think fun idea for a potential future collaboration if anybody's interested in reimagining how we can turn roadways into carbon dioxide removal centers. And with that, I want to thank collaborators. Large number of collaborators, as had Chris Reinhardt, Georgia Tech, Shuang Zhang, and Yoshi Kazaki were critical in all this, and Jake Jordan and David Bierling are also key collaborators in this. And I will leave it there to see if there are any additional questions.
Well, fantastic. Thank you very much. Probably the biggest open thing, I think, in the whole story was the measurement verification. What are the challenges, and to what extent do we have, I mean, both models and just probes and measuring devices for checking how much weathering has occurred?
Yeah, great question. I think the short answer is there's a tremendous amount of interest right now in scaling this up, and making sure we have an MRV framework is a key question. So a lot of my time is spent modeling. A lot of my time is also making sure that we have measurements and making sure that in the long term we can move from what will be essential for cost is an MRV framework that is largely model based, but we first need to have empirical measurements that are expensive that tell you the amount of weathering, for instance, is happening that we can use to test how models are working. So we're at the stage right now where we don't have a really efficient MRV framework. It's measurements that are expensive to make, and we don't really know for a large number of regions how many measurements, so how much it costs to actually track these carbon fluxes.
So are we talking, is the state-of-the-art soil carbon measurement?
So this is very different than organic carbon.
Right, because I know that's expensive.
Yeah.
I'm not sure how more or less difficult this is.
Yeah, so at this stage, it's in some ways it is similar to soil organic carbon, where you are making empirical measurements at fields that are telling you the amount of weathering. There's some aspects that make this much more straightforward than soil organic carbon sampling, because that is reversible through time and varies with depth in a way that you don't have to account for enhanced weathering. But the simple takeaway from that is we want to move to a case where we can model this. We need empirical measurements to see how well we're going to do that. Any empirical measurements are expensive.
Okay, so let me then get this. So suppose we had, this is now in, what do you care about MRV? A lot of it is for carbon offsets and just validating that you've done what you claim to have done. If you had many measurements during a large-scale deployment, in some ways, if offsets come later after you've done the measurements, you could bootstrap it. I mean, is that fair? If you had a big enough deployment, you would. These are the measurements you would need for the model.
Yeah, I mean, to kind of to not answer your question directly, I think what we need right now is we need people buying large amounts of offsets, like Alphabet, to realize that many forms of carbon dioxide removal that have been purchased are not going to ever give you carbon dioxide removal. There's no way to know what is the fate of some organic carbon on a more than 10-year basis, and dioxide stays in the atmosphere for over 1,000 years. So for corporations that are leading the charge in doing this and ensuring that there's a carbon dioxide removal market, need to invest in, I would say my bias is that they need to invest in figuring out what is the potential for more durable types of carbon dioxide removal that can be cost effective. Enhanced weathering is one of those. And that's going to mean potentially less credits purchased early on and a cost moving down as we have a better understanding from that.
Right.
And so then, not all of these, of the myriad of new ways of carbon dioxide removal that have been proposed, we also need to be open to the idea that not all of these are going to work. I think enhanced weathering has tremendous potential, but right now, I think one of the things, instead of focusing only on what is the cheapest way to buy carbon credits, we need to refocus with a large amount of disruption in the carbon dioxide removal market, reground ourselves and focus on what is going to deliver actual robust carbon dioxide removal. How do we know, and how do we gauge meaningfully the uncertainty in that?
Got it. And then probably just one more question. What is driving the costs? And as you're saying, they're going to drop. What is going to, do you expect to be driving the drop?
Yeah, well, I mean, so there's basically, as you increase scale, you're going to have, you know, efficiency associated with that. As this becomes more widely adopted, that will just increase the efficiency of the deployment. And then the other one is the MRV cost. Ideally, what you want to move is something that is all empirical driven to a combination of model driven with spot checks with empirical observations to give you uncertainty. That will make it cheaper. And that's something that we're only going to be able to do if we put in money up front to gauge how well this works and how well we can predict it.
And but is it because now, like the mining, the transportation from mine to the much more diverse set of fields, or the actual deployment on the fields, or something else?
It's the deployment, the moving the material to the fields is the main cost. So, and that's one that, you know, it's scale. The number that you have, people often, what does it cost? That's scale dependent. If you can have things where it can be incredibly low cost, where it's right next to a mine.
Yeah.
And then you can have things where if you move it very far, it's going to be a high cost.
Oh, sure. Speaking of which, so you focus on basalt, but there's olivine and there's other minerals. How
exactly I
distributed are these things?
Basalt, but we should think about it in terms of a wide range of different minerals, and there's different companies that are doing different deployments.
Okay, so then maybe the very, very last thing is, are you aware of the techno-economics models of saying where are these things spread out across the globe, and where the fields are going to be spread out? So that more, that kind of model.
Yep, we've done techno-economic. I've published on techno-economic assessments, and it's fun where that's great to do. Again, to get a better understanding of that, we're gonna have to put water through the pipes and see how it actually works instead of a desk-based estimate.
Right. It makes sense. Well, yeah, thank you very much. It's fascinating.
Thank you.